We're going to talk about acid reaction chemistry. There's three main types of acid reaction chemistry. Those where we have an acid reacting with a base, that's either a hydroxide or an oxide, acid reacting with a metal, or acid and a base that's a carbonate, a CO3 negative. Now, in each of these, there's specific products that we can expect to get out of them. So we're going to go through all of them. First of all, we want to think about acids, and acids are something that have, generally speaking, a hydrogen ion, which we know is an H1 plus, unless hydrogen is bonded to something uncommon like a metal, then we know that that oxidation state changes. The hydrogen reacting with some non-metal, some anion. Remember, anions are a negatively charged ion, and those are our non-metals. So let's say, for instance, in their first case, we have hydrogen with a 1 plus reacting with a Cl1 negative. In other words, hydrochloric acid. If I look at the oxidation states of the hydrogen and the chlorine, I see that their overall would be just one of each for it to be a neutral 0 overall. So we'll write HCl for hydrochloric acid. I could put an AQ behind it representing that it's aqueous if I wanted to. And that's going to react with a base. And in this instance, I'm just going to pick a common base that we use. One of the most common that we've used in the lab is sodium, which we know is an alkaline metal, so its oxidation number is a 1 positive, and the hydroxide ion, sodium hydroxide ion we know is a 1 negative. Those polyatomic ions have set charges or oxidation states. So I would write that as sodium hydroxide NaOH. Now what I get is always two things. I get water coming from the hydrogen of the acid and the hydroxide of the base, H2O, plus a salt. And the salt's going to be all of the leftover stuff. So in this instance, I've got sodium and chlorine. I want to look at charges again, and they're not going to change, so I wrote them already there. Sodium is still going to be a 1 plus as the oxidation state, and chlorine is still going to be a 1 negative. Those halogens with a more electronegative value is going to stay their common value. And so we would have NaCl dissolved in water or aqueous. And then I take a look, I've got one hydrogen, that's two hydrogens, and I've got two over there. One chlorine, that's balanced. One sodium, that's balanced. One oxygen, that's balanced. So I've already got an already balanced reaction. Now, if this had been something like sulfuric acid, H2SO4, I would still have water as one of my products, and I would take into account the fact that I have two hydrogens there and one there when I do balancing. So it's not going to change this product, and it's not going to change my salt. My salt is going to be based off of the oxidation states of the metal anion and the non-metal cation. And just a reminder, we always write the metal first, or the cation first and the anion second, whenever I'm writing out those words. Let's take a look at another one. And why don't we use the sulfuric acid that we were just looking at, H2SO4? Hydrogen being a 1 positive oxidation state, and sulfate, the polyatomic group, being a 2 negative. Cancels out, and we get H2SO4. Again, that would be aqueous. And let's just pick any old metal. Let's use magnesium, which we know is an alkaline earth metal, so its oxidation state when it's in a compound would be a 2 positive. Would lose those 2 electrons in its valence shell quite easily. So what I form whenever I have an acid and a metal reaction is hydrogen gas, which we remember is always going to be diatomic when it's on its own. One of the lucky 7. We've got the hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, the magic 7. And we also have the leftover stuff, just like we did before. This time I've got the metal being my cation, and then the polyatomic sulfate group here as being my cation. Oop, I just said the wrong one, anion. So Mg is a 2 plus, SO4 is a 2 negative. So I can see from the oxidation states that I will need one magnesium to cancel out with one sulfate group. So that's nice and easy for me, MgSO4. Then I can take a look to see if I'm balanced. I've got 2 hydrogens here, 2 hydrogens here, 1 sulfate group here, 1 sulfate group there, 1 magnesium there, 1 magnesium there. This one happens to be already balanced as well. Now we're going to take a look at an acid and a base with a carbonate, or I could have just as easily written a hydrogen carbonate. Hydrogen carbonate, which is an HCO3, 1 negative. So let's take a look at an example here. And let's pick something a little bit different. H3PO4, some phosphoric acid. H3PO4. We need 3 hydrogens to cancel out as their 1 positive charge, so H1 positive, with the PO4 oxidation state of 3 negative. So I need 3 positives to cancel out with the 3 negative, and that's why I have that subscripted 3. And I'm going to react with it sodium carbonate. So sodium, again, is an oxidation state of 1 plus because it is an alkali metal. Carbonate is a CO3, 2 negative, so I get Na2CO3. And that's going to form 3 products this time. The other 2 had 2 products, the H2O and a salt, the H2 and a salt, and this one's going to be CO2 plus H2O, those 2 are always going to be givens, plus a salt that I'm going to have to figure out what that salt is. So where are all of these things coming from? Let's take a look at the CO2 first. The CO2 is coming from part of the carbonate, so that's where I'm getting that from. And the water is coming from the hydrogen and the oxygen of the carbonate. And then I look at what's left over. So I have a sodium and I have a phosphate group. Again, I'm going to list the metal or the cation first. Na has an oxidation state of 1 plus. Phosphate is a PO4, 3 negative. So to get this to be a neutral compound overall, I need 3 of my sodiums with a 3 positive to equal out the 3 negative of 1 phosphate mole. So I have Na3PO4. I can see this is my first instance where I haven't had a balanced equation, and I'm going to give you a moment to figure that out on your own, and I'm going to end this recording because you have listened long enough.